Hello everyone, and welcome back. Today we're going to talk about angular or rotational impulse. And we're going to start right off the bat with a derivation and a bit of a recap on linear impulse. And to do that, I'm going to start right off by putting up some equations that we are quite familiar with. Acceleration is F over mass. This is Newton's second law. Acceleration is change in velocity over time. This is based off the very definition of acceleration. Angular acceleration is net torque over moment of inertia. This is angular second law. Angular acceleration also equals change in angular velocity over time. I'm going to take this section right here and I'm going to cross multiply. When I cross multiply this way, I get force times time equals, and when I cross multiply this way, I get mass times change in velocity. I'm going to do the same thing over here. Torque times time equals moment of inertia times change in angular velocity. Now, since momentum is mass times velocity, this is mass times change in velocity. Therefore, this is change in momentum. And you may remember, change in momentum is impulse. Angular momentum is moment of inertia times angular velocity. This is moment of inertia times angular velocity. Therefore, this is angular impulse. To change the momentum of something, you need to exert an unbalanced force for a period of time. If you want to change the angular momentum of something, you need to exert an unbalanced torque for a period of time. From a conceptual perspective, these are near identical. It's just that one is linear and one is angular. Taking a look at the units here, force times time is Newton seconds. Mass times change in velocity is kilograms times meters per second. This is the units for impulse, and this is the units for linear momentum. Technically, either of these could be used as the unit for impulse depending on how you're looking at it. However, only the unit on the right can be used for momentum. Over here, torque is force times radius. Since torque is force perpendicular times radius, that means our units are Newton, meters, seconds. On the right, moment of inertia is kilograms meters squared. Angular velocity is radians per second. And since radians are basically a fake unit, it's usually written like this. So units for angular impulse can be newtons meters seconds or kilograms meters squared over second squared, which is the unit for angular momentum. All right, now that we've derived angular impulse, let's do a few quick problems just to get the idea across. The first one's going to be pretty conceptual, but the idea comes up quite often. Okay, so I have this little playground toy. You grab the handle here and you spin it and it spins around and around and around. This is the exact same toy except it has a bunch of kids on it. So here's our problem. An adult exerts the same torque for the same period of time on both of these. Which one ends up with the higher angular velocity and which one ends up with the higher angular momentum? For the sake of simplicity, we'll call this side A and this side B. Now, since we're talking rotationally, one of the first things we're going to notice is the moment of inertia of A is definitely smaller than the moment of inertia of B. It's the same device. B both has more mass and more mass toward the outside edge. I'm going to put up my angular impulse equation. Okay, first question, which one ends up with the higher angular velocity? We're going to assume, since the way this question is asked, that initial angular velocity is 0 radians per second. So in other words, it starts at rest. So this is gone. If I rearrange, I get final angular velocity is net torque times time over moment of inertia. And this basically gives us our answer right here. The problem flat out says that the net torque and time are the same. Therefore, the one with the smaller moment of inertia is going to have the higher angular velocity because it's in the denominator. In other words, this is a part of the question where people just get naturally. There's no kids on this. So if you exert the same torque on both of these for the same period of time, of course this one's going to be spinning faster. So A is going to have the higher angular velocity. The one that catches people is number 2, which one is up with the higher angular momentum. And the mistake people make is that since A will be spinning faster, it has a higher angular momentum. However, the problem very specifically states it's the same torque for the same period of time. And this literally equals change in momentum. So another way to put this is angular momentum final minus angular momentum initial equals torque times time. This is the same, and there is no initial angular momentum. So final angular momentum is simply torque times time. We know these are the same, so the answer to question number 2 is that they will be the same. So therefore, they will have the same final angular momentum, or A equals B. All right, let's set up a problem that actually has some values. So here I have a metal bar, and I have 2 rockets attached to the metal bar. the metal bar has an axis which is dead center here. So this is the axis of rotation. When the rockets turn on, they will spin the metal bar in a counterclockwise direction. Here is our problem. Two rockets are attached to a 5 kilogram metal bar. The bar is 6 meters long, and the force provided by each rocket is 12 newtons. If the bar starts at rest, how much time would it take to reach an angular speed of 30 rotations per second? All right, we are going to start how we always start, which is listing givens. Mass of the bar is 5 kilograms. Force of each rocket is 12 newtons. Length of the bar is 6 meters. I'm using lowercase l so I don't confuse you with angular momentum. Considering the axis is dead center of the bar, I'm immediately going to put the radius as 3 meters. Starts at rest, so the initial angular velocity is 0 radians per second. Final angular velocity is 30 rotations per second, which is 60 pi radians per second, which can also be written as 188.5 radians per second. And since we're about to use the impulse equation, we do have to be in SI units here. And mostly because torque is force perpendicular times radius. I'm going to move up my equation. Torque times time equals moment of inertia times change in angular velocity. There is no initial angular velocity. I'm after time, which is moment of inertia times omega final over the torque. I have omega final, which means I need these two. Torque is force perpendicular times radius. Force is 12 newtons. Radius is 3 meters, which is 36 newton meters. However, since we have two rockets, both at a 3 meter radius and both are perpendicular to the lever arm, we're going to multiply that by 2, which gives us a torque of 72 newton meters. Now, another reason why I chose this is because we don't know the moment inertia of this situation. We know the point mass, ring, disk, and sphere. And as I said earlier, not really expected to know this. Typically, if it's an odd situation, it'll be given to you, or you will need to look it up in a chart. For a bar like this, the moment of inertia is 1/12 ml squared, which is 1/12, 5 kilograms, 6 meters squared. Notice it does not use R, it uses L, which gives us 15 kilograms meters squared. That is our moment of inertia. I can now put that over here. 15 kilograms meters squared times 188.5 radians per second over 72 newton meters. A newton is kilograms meters second squared. That means the kilograms cancel. One of these meters cancels here, the other meters cancels here. Radians is a placeholder unit, does not exist. This is now 1 over seconds squared, which flips because it is in the denominator. Then one of these seconds cancels. The only thing left is seconds here in the denominator. So now in the denominator, I have 1 over seconds, which is going to flip, and I get 39.3 seconds. This is how long it would take these two rockets at this distance and with this force to speed up this bar with an angular acceleration to a rotational velocity of 30 rotations per second. And once again, as long as you're organized and can list your givens and follow proper steps and keep things organized, it is pretty much like following a trail of breadcrumbs. Okay, the last thing we're going to do is fill in our linear rotational chart. Impulse is force times time equals mass times change in velocity. Therefore, angular impulse is torque times time, which equals moment of inertia times change in angular velocity. And now we have another one on the list. All right, make sure you add to this chart in your notebook. I will end it here. Other than that, have a good day. This is Mr. M signing off.